We've learned a lot about taking derivatives, and that's going to come in handy in this section because I'm going to be looking at functions where a derivative is necessary in order for me to find the integral. One thing to keep in mind with this particular section is that with integration, not all things can be integrated, not integrated easily or found an antiderivative of, whereas with differentiation, I can take the derivative of almost anything given enough, persistence and rules, I can find the derivative, but integration and antiderivatives are a little bit different. So let's go ahead and start with one example. Now for this particular example, you can tell it's an indefinite integral right here because there's no limits of integration. And let's look at x squared plus 19 to the 20th dx. Now knowing what I know now about integration, I could do this problem if I wanted to expand this 20 times and then distribute through the 2x. So this is doable with a lot of work. However, there's a little bit shorter way we could do this with a rule called U-Substitution. So that's what we're going to be focusing on today, is to be looking at some other functions that we can actually find the antiderivative of using U-Substitution and an idea called change of variable. So if we look at our power, or our base here, I can see that my power is x squared plus 19. So if I let u equal x squared plus 19, let's see what would end up happening here. That would mean that this piece would be u to the 20th. So let's go ahead and start with that substitution. So I'm going to have a 2x, and then I see pretty clearly here that this would be u to the 20th. And this seems like a pretty nice improvement so far, except I still have this dx I need to worry about, and I need to have this 2x gone. The 2 can stick around, but the x can't. When I integrate, I can only have one variable of integration with respect to x here, unless something else is considered as a constant. So I come back up here and I think, okay, well, u is equal to x squared plus 19. What would be du dx, the derivative of u with respect to x? Well, that would be 2x, derivative of 19 is 0. And then if I solve for du, I'd multiply both sides through by dx. I'd get 2x dx, and I have that right here. I have 2x dx. So when I rewrite this integral, it ends up to be u to the 20th du. Now that is a doable integral. You just go ahead and add 1 and divide by the sum. And there's your solution, except I need to change it back to the variable x. So I need to convert back. U again was x squared plus 19. It's now to the 21st over 21. Plus c, my constant of integration, because it's an indefinite integral. Now I could check this as well, and it's a good idea to get into the habit of checking these. Some of them get kind of ugly to check, but this one's not too bad. X squared plus 19 to the 21st over 21. So I'd bring the 21 down, decrease the exponent by 1, and then I'd multiply it by the derivative within. This is the chain rule. So again, I'm taking the derivative, and this is all over 21 from here. You bring the 21 down, decrease the exponent by 1, multiply it by the derivative within. And again, this is the chain rule. The 21s cancel, and you can see that I'm left with x squared plus 19 to the 20th times 2x, which is my original integrand. So this one checks, and again, it's a good idea to check these when you can. Some of the derivatives get pretty ugly, but they will establish that it is correct. Now for an indefinite integral, most of your calculators will not check an indefinite integral. They only work with definite integrals. So these are pretty fun to work with, and they're really fun to work with when you're using trig functions. So let's go ahead and look at a few with trig functions. We'll look at another indefinite integral. Let's look at the integral of negative 10x. Let's do sine of 5x squared plus 4 dx. So again, I could integrate sine, and I could integrate it with a negative 10 out front, but what I can't do is this x and then this argument of the sine. So what I need to do is think about my highest power. In this particular case, it's 5x squared plus 4. And I was doing the same thing up here. The highest power was x squared plus 19, and you might say, well, wait a minute, to the 20th. But I'm looking at kind of the base functions, not the exponent function part. So we do U-substitution on this one as well. So u would be the argument of my trig function, 5x squared plus 4. then du would be 10x dx. And again, I get that by multiplying both sides through by dx to get that popped up there. And you can see I do have that. I have 10x dx is here. And then this part right here would be the sine of u. Now what's left over is this negative, and so I'll have to pull that out front. So I have negative integral sine of u du. So dragging along the negative, the integral of sine is going to be a negative cosine. And again, you have to know these from your antiderivatives. Minus a negative is the same as a positive. So I get cosine of u here, but that's not my solution yet because I need to sub back in. My original was in terms of x, and so should my solution be when I get done. So this is 5x squared plus 4. And as usual, please put parentheses around the arguments of your trig functions. Don't forget your constant of integration because this is an indefinite integral and there's a whole family of antiderivatives and not just the one. Okay, so to look back real quick, we're looking at the integral of sine. The integral of sine is a negative cosine. This minus sign came from the original equation when we weren't able to use that. So again, knowing your antiderivatives is going to be very important, especially for your trig functions. Let's look at another trig function. Let's look at x to the 6th times the cosine of x to the 7th dx. So again, my highest power is x to the 7th. And the reason I look for my highest power is when I take a derivative, the power decreases. So let's start with u equal x to the 7th. Du would then be 7x to the 6th dx. Okay, and again the du dx, and then I multiplied both sides by dx. And if you notice, I've got this. This is cosine x to the 7th would be cosine of u. And then this x to the 6th dx, I have that as well. Here's part of it right here. But I'm missing a bit. I'm missing the 7 out front. So I have to do something called compensation here. And you can do this many different ways. Some people use substitution. I like to use compensation. So I look at this and I think, I'm going to compensate for this missing 7. Well, if you multiply by 7, you can't just multiply by 7. You have to have the multiplicative identity, meaning you can multiply by 1. Well, 7 over 7 is 1, so I can just pull that 1/7 out front. Now if you notice, 1/7 times 7 cancels, and really the only effect here then has been multiplying by 1. So when I rewrite this, I have a 1/7 out front, the integral of the cosine of u, and then collect all my other terms, du. The integral of cosine is going to be a negative sine. Whoops, sorry. The integral of cosine is going to be a positive sine. But my original was in terms of x, and so should my solution be. So I need to go ahead and sub back in with my x's before I can say that that's my final solution. Now I got a little bit mixed up about that integral of the cosine, so let's go ahead and check our answer to make sure I don't have a mistake. So I have 1/7 sine of x to the 7th plus c. I'm going to take the derivative to check this. So I drag along the 1/7. The derivative of the sine is the cosine of the argument times the derivative of the argument, which would be 7x to the 6th. The derivative of a constant is 0. The 7's cancel, and let's see what we're left with. This looks like x to the 6th cosine x to the 7th, which was my original, so it did check. I did get my antiderivative correct. So that's a quick way that you can, check your work. Give it a second and check your work. So here I had to compensate for the missing 7 by multiplying by a 7 on the inside and then compensating for that with a 1/7 on the outside. So we've looked at a few functions. We've looked at some trig functions. We've looked at compensating for a missing coefficient. Let's go ahead and look at another one that's getting a little bit more complicated. And again, you always try and look for the base function that I can take the derivative of to work from there. Now this is no power rule is going to help us out here, so I know right away I'm going to use U-Substitution. I'm going to look for the function that has the highest power, and that would be 3 minus 8x to the 5th. Now I don't want to take the 1/2 with it. These are composite functions, and I just want the base or the original of that composite function. du, the derivative of 3 is 0. The derivative of negative 8x to the 5th is negative 40x. So we'd bring the 5 out front and then decrease the exponent by 1 dx. Now as I look up here, I see that I have a 2x to the 4th, but I need a negative 40x to the 4th. So I can think about multiplying by a negative 20 on the inside, compensating with a negative 1/20th on the outside. Now this looks like it's getting worse, but actually it's better, because once I go ahead and sub in then negative 20 times 2 is negative 40x to the 4th dx. That's just du. And in my denominator, 3 minus 8x to the 5th is just the square root of u. And then I rewrite this, I flip that up top, so I can use my good old power rule. And then I add 1, divide by the sum. I'm ready to integrate now. So I add 1, divide by the sum. So I have my negative 1/20th out front. When I divide by a 1/2, that's the same as multiplying by a 2 over 1 up top. And of course, u to the 1/2 is the square root of u. Canceling, 2 goes into 20 10 times. And I have a negative 1/10 square root of u. But u was 3 minus 8x to the 5th plus c. Now again, if you want to take a derivative of that to check your work, you can, and especially on a test you should kind of get in the habit of doing that. It's a good way to check. Let's look at a problem that probably is not going to really be as straightforward. You might not see the substitution first. So on some of these problems, what I'll do is I'll get you started with the substitution and kind of let you take it from there. I want you to kind of get good at choosing the correct substitution. So let's look at the integral of the square root of x plus 6 to the 7th power. And this is all going to be over 2 root x. Now if I wanted to, I could try and expand this to the 7th power, and then divide through by 2 root x. But that's a pretty long process. So let's see if we can use a U-substitution here. So U-substitution, I would let u equal square root of x plus 6. That's the same as x to the 1/2 plus 6. du then would be bring the 1/2 down, decrease the exponent by 1. The derivative of 6 is 0. And of course this was du dx, and then I just multiply both sides by dx. And then simplifying, I get 1 over 2 root x dx. And you can see then, when I rewrite this, I have a u to the 7th, and then all of this piece becomes du. It's not in the denominator, because this is 1 over 2 root x dx. All of this is du. And then you can integrate from there. So again, I want to spend some time setting up some of these problems to help you out. I'll leave the integration to you for some of them. For our next one, I think you could get this one without help, but I'm going to give you a good start on it. We would have nothing in my numerator other than dx, and then in my denominator I have 3x minus 1 quantity squared dx. So we let u equal 3x minus 1, du is equal to 3 dx. So this is an example where I have to compensate. I'm missing that 3 coefficient up top. So if I multiply by 3 to compensate, I have to divide by 3 on the outside, which is the same as multiplying by a third. So when I do my substitution, this 3 dx, I guess I don't need 2 of those dx's, this 3 dx becomes du. My denominator becomes u squared. And I usually like to rewrite these as not du over u squared, but 1 over u squared du. I always like to keep in mind that this is the height of a rectangle, this is the width. So to integrate this, I'd have to pop this up top and then add 1, divide by the sum. And remember, you have to make sure that when you're done, you compensate by substituting back in for x. If your original is in terms of x, your solution should be as well. This next problem, there's a little bit more to it than just a straightforward U substitution. This is called a change of variable. These are one of my favorite types of problems. We'll spend a little time on these. So if we look at a problem, we're going to see very quickly that U-substitution doesn't quite work. So we're pretty good at these now, so we would say, okay, let's let U equal x plus 2. du then would be 1 dx. Okay, so let's see what that leaves us with. X plus 2 is u, so this would be u cubed in the denominator. Dx is directly replaced by du, and then I'm left with this x. And so that's when U-substitution fails me, because I'm left over with this x. Well, what we do is we come back up here and we say, oh, well, I know what x is. I solve for x here and I get x equal u minus 2. So that's my change of variable. I'm changing these over from x's to u's, and then I have to do this extra little change right here to finish the problem off. So u was equal to x plus 2, which means x is equal to u minus 2. So I've made that substitution. Now for this problem, the easiest way is to separate the denominator. You can never separate the numerator unless, to separate the numerator, you can never separate the denominator unless it's just a monomial like this one is. And then I simplify. U over u cubed would be u to the negative 2. This one I'd flip the u up top, and then I'd integrate. So I'd add 1, divide by the sum. Add 1, divide by the sum. And I think I need to simplify quite a bit here. This u to the negative 1 flips down. So I have negative 1 over u. The 1 stays up top, and I just move the negative up top to make that a little easier. The 2's cancel. So the 2's cancel. A negative times a negative is a positive. So I'm left with 1 over u squared. Now this is not my answer yet. My answer has to be in terms of x. So I'm going to finish this one up here. I don't think that I want to convert quite yet. I don't want to convert. I want to find a common denominator. And that's just because when we simplify, I mean simplify completely, find common denominators, factor completely, everything. So I'm going to multiply top and bottom by u. I'll be left with negative u plus 1 all over u squared. And now I can sub back in u is equal to, come back up here, u is equal to x plus 2. Now when I do that, you can see that some things will cancel. So I have negative, I have to put parentheses up to make sure I subtract the entire value of u, which is x plus 2, all over u squared. But oh wait, we know what u is. It's x plus 2. Can't cancel these x plus 2's. So I have minus x minus 2 plus 1 all over x plus 2 quantity squared. So I have minus x minus 1 all over x plus 2 quantity squared plus c, don't forget your constant of integration, to represent an entire family of solutions for an indefinite integral. Now if we wanted to, we could check this by taking a derivative. You can see our derivative is going to be a quotient rule. And then once we get done, and we might have to simplify it a lot, it would eventually get back to this point right here, x over x plus 2 quantity cubed. So if you're thinking like you might want to take some derivatives, this would be a good one to try. That was a change of variable. So a lot of times the problems that we're looking at, once we get them started, they're really not that bad to work with, but getting them started is kind of the tough part. Now so far we've always been using x's and u's, but that's not always going to have to be the case. You could use v's and w's and all sorts of other variables. So let's go ahead and do a problem where we're not using a u or an x to get started with. Since my variable here is v, everything has to be in terms of dv. Now notice these larger parentheses are telling me exactly what my integrand is, and it's also showing me that, let me make sure I get them in the right spot here. It's also showing me that the sign of v gets distributed through that trinomial. So the way this is written now, If I let u equal this entire trinomial, I definitely don't have a du. But if I do a little work and distribute this sign to each of the terms of the trinomial, I'll have a setup to start with u-substitution. So this would look like negative cosine 5, cosine to the 5th of v, sine of v, plus cosine v sine v, plus 1 times sine v is just sine v, and all of this, of course, is dv. Now it looks like it's worse, but it's actually better because now I can use u-substitution on each piece. I'm going to look at this as negative cosine to the 5th, so that negative is actually out front. Let me rewrite that. Negative cosine of v to the 5th times the sine of v. So that's one integral, plus the integral of cosine of v sine of v dv. There's another integral. And my last one is sine of v dv. Well, let's pick the low-hanging fruit first, and let's do this last one. The integral of the sine is going to be a negative cosine of v. That's just the fact that it's an antiderivative. Now, along the lines, let's go ahead and use a u-substitution on all the others. So this is part of my solution, and I need to remember it. So for here, I'll use u is equal to the cosine of v. Du is then equal to the negative sine of v dv. I'm missing the negative, but I have the sign, so I'm going to compensate with a negative on the inside and a negative on the outside. And then I see this is really the same thing, but I have my negative here, so I don't have to compensate. So rewriting, this looks like I have u to the 5th, and then negative sine v dv is my du. Negative times a negative, I don't want to think about it like that. I just want to think about this negative out front, because this negative has to go with this sign in order to create du. So this is just u du. And of course, I'm already done with this piece, minus cosine of v dv. So this is not part of an integral, it's part of my solution. So integrating, I get u to the 6th over 6th minus u squared over 2 minus cosine of v. I have to substitute back in. U was the cosine of v, so this is cosine to the 6th of v over 6th minus cosine squared of v over 2 minus the cosine of v plus c, my constant of integration. Now I could simplify this a bit. I could find a common denominator and write it as a single fraction over 6. And I could also factor out a cosine of v, but for this one, we'll call that good because those simplifications won't lead to any further simplifications like being able to combine any like terms. So again, while you're working these, you have to use a little bit of imagination to get to the correct rewrite. And so for the next couple, I'll just go ahead and get you started with the correct substitution and leave the integration up to you. For this one, let's look at the secant of w. Let me make that look like a good w. Plus 5, let's say, to the 8th times secant w tangent w dw. Now this is just a big old mess. Right away we wanted to think, okay, so u-substitution. The base of this power is secant w plus 5. So let's let u equal secant of w plus 5. Du, the derivative of secant, is secant w tangent w dw. Now the dw comes into play because I'm taking the derivative of u with respect to w, and then I'm multiplying through both sides by dw. Now if you do this, we end up with the integral of u to the 8th du. Okay, so I'm going to get you started on that one, and you can go ahead and finish it up. Now we've already talked about change of variable, so always be having your eyes open for a change of variable type problem. This is a change of variable that I think that will work all the way through. So again, this one, change of variable. These are my favorite kinds of problems. So for this change of variable, the last one we looked at had a numerator and a denominator. And with change of variables, that can often happen, but it doesn't have to always be a numerator and a denominator. So let's look at this example. Let's look at x times the fourth root of 3x plus 1 dx. So we're pretty comfortable with saying, yeah, it looks like u should be 3x plus 1. Du would then be a 3 dx. I don't have a 3, so I'd multiply by a 3 on the inside and compensate with a 1/3 on the outside. So as I'm writing this up, this 3 goes with the dx, so it looks like I'm left with an x. And then I have this 3x plus 1, which would be the fourth root of u du. So I'm left over with an x, and this is the big signal that I need to do a change of variable. So if I were to solve for x over here, I'd get u minus 1 over 3. Okay, so I need to plug in for that. Integral. Now in place of that x, I'm going to have u minus 1 over 3. And then this u to the 1/4 would be the fourth root of u du. So this is what I'm ready to integrate. Now 1/3 times 1/3 I can pull out front for a 1/9. And then I have u minus 1 times u to the 1/4. That would be u, I'm going to take this and distribute, to the 5/4 minus u to the 1/4 du. And now I'm ready to go through and add 1, divide by the sum. So 5/4 plus 1 would be 5/4 plus 4/4, which is 9/4, divided by 9/4, minus u to the 5/4 divided by 5/4. And then of course we have some plus c there as well, but we're not going to worry about the constant of integration until we get to the end, because I need to simplify this and then get it back in terms of x. Okay, let's go ahead and keep rewriting and simplifying. I have that 1/9 out front. When you divide by a fraction, you multiply by the reciprocal, so this would be 4/9 u to the 9/4. When you divide by a fraction, you multiply by the reciprocal, this would be 4/5 u to the 5/4. Now I see pretty clearly that we could pull a 4 out. So let's go ahead and do that. Let's see what we have left. I also have a u that I could pull out. Let's pull the u out too. I have u to the 5/4 that I could pull out. So then I'd be left with 1/9 u to the first, because 5/4 plus 4/4 is 9/4, minus 1/5. And then the rest of this is just a bunch of fun algebra. So my common denominator here would be 45. So I'd multiply top and bottom by 5, so I'd have 5u minus, multiply top and bottom by 9, all over 45. So I have 4/9. I'm going to pull that 45 out too. So I have 4 over 9 times 45, u to the 5/4 times 5u minus 9. Now I'm ready to sub back in. And I'll sub in that u is equal to, I don't remember, u is equal to 3x plus 1. And again, showing your work is so important here because that's where you're going to get your credit from. So denominator, 9 times 45. So 9 times 45 would be 945. Getting some big numbers here. U was 3x plus 1 to the 5/4. And then I have 5 times 3x plus 1 minus 9. Still not done. Fun's not over. We're going to take the 5 and distribute it and combine like terms. I'll have 15x plus 5 minus 9. Looks like there's a little bit more that we could combine. So 15x, 5 minus 9 is negative 4. So there's my final solution. I need a plus c for my constant of integration. There's several different ways that we could rewrite this. I think I'll write this as 15x minus 4 over 945. times 3x plus 1 to the 5/4 plus c, my constant of integration. So when you're working with these and simplifying, you really need to think about simplifying things completely and getting it into a form that I can actually work with. If I wanted to take the derivative of this, I would use some sort of a product rule with a chain rule involved as well, and then simplify the heck out of it to make sure I got back to my original integrand. So once we got done with the calculus here, a lot of it was just straightforward algebra. Okay, let's go ahead and, whoops, I think I see a mistake as I'm scrolling through here. So here I have 9 times 45, 9 times 45, and then I see in my next step I just wrote 945, but this is multiplied, so this is actually 400, 9 times 40 is 360, yeah, this is 405. So I just wrote it down without the parentheses instead of actually multiplying those two numbers out. I'm glad I caught that. Otherwise you guys would have been wondering what's going on. So it'd be 405. Okay, so let's go ahead and look at a few more integrals. And again, when we're looking at these, sometimes we'll just set them up to get you started and let you handle the integration after the U-substitution, and sometimes we'll work them all the way through. If we look at a problem, well, this one will be interesting. This one's going to be interesting because we're going to have limits of integration. So this one is different. Let's work this one all the way through. So let's go 0 to pi over 2. So this is the first time we've had a definite integral. So 0 to pi over 2 sine squared of x cosine of x dx. So integration, definite integral. I have two options. I can drop the limits of integration and then stick them back in at the end, or I can change the limits of integration, and that would mean changing them to in terms of u. So I'll do this problem both ways, and you can see that either problem or either way works. We will just have to, you guys have to decide which method you'd prefer, and you just need to make it clear what method you're using. So I'm going to use my first option here. I'm going to drop the limits of integration. And again, you can choose which option you like best after you see them both. So when we're talking about dropping my limits of integration, we do just that. I'm looking this sine squared of x cosine of x dx. So we're going to let u equal sine of x. Du, the derivative of sine, is the cosine of x dx. And then this turns out to be just a nice little u squared du. Now I've totally dropped my limits of integration. They're gone. One other thing I guess that we could do here is just to clarify, we could say, well, x equals 0 to x equal pi over 2. So down here I could have x equals 0 to x equal pi over 2 as well. But notice I have to have the x here, because if I don't have the x, I'll assume that they're u's and they're not. Another thing is just to drop them and forget about them. So when we integrate, we add 1, divide by the sum, and then I switch back to my variable, my function in terms of x. So this would be sine cubed of x over 3. And now here comes the limits of integration again. X equals 0 to x equal pi over 2 is what I plug in. I'm going to pull the 1/3 out front, and I'll have the sine of pi over 2 quantity cubed minus the sine of 0 quantity cubed. The sine of pi over 2 is 1, so this would be 1 cubed. So the sine of 0 is 0, so 1 cubed minus 0 cubed is 1. 1/3 times 1 is 1/3. So that's option 1, drop the limits of integration. Okay, let's look at option 2, change the limits of integration. Now when we change the limits of integration, what happens is I don't have to convert back to x's. So what we would do is we'd have our problem. We'd have sine squared of x cosine of x dx, and these would go from 0 to pi over 2 as usual. But then when I start my U-substitution is when things change. So u is sine of x, du is cosine of x, that's all good. But then, if u is sine of x, what's going on when x equal pi over 2? What's going on when x equals 0? Well, when x equal pi over 2, the sine of pi over 2 is 1. When x equals 0, the sine of 0 is 0. So those are my new limits of integration. So now I'm going from u equals 0 to u equal 1 of u cubed, I'm sorry, that's after you integrate it, u squared du. So you integrate, you add 1, divide by the sum, and I don't have to convert back. Now I just plug right in. So I'd end up with 1 cubed over 3 minus 0 cubed over 3, which is 1/3. So you get the same thing either way, whether you drop the limits of integration, switch back to x, and then plug them back in, or if you change your limits of integration right away up here in your step where you do your U-substitution. And it simply doesn't matter which choice you do. It just doesn't matter. Just make sure that you show all of your work to make sure that you can receive all the credit possible. Okay, so I think we've looked at most of the different types that you'll run around in this homework set. Sometimes you'll be given a story problem, and instead of setting up the integral for you, they'll ask you to find the area of the region bounded by a graph. So let's go ahead and look at one of those types. And let's do the graph f of x equals, let's do another trig function. We're probably doing too many trig functions. X sine of x squared between, let's do x equals 0 and x equals square root of pi. So to get started here, I don't really even need to look at a graph. All I need to do is to think, okay, I'm trying to find area, and it'll be net area, of this function. So this is the height of the rectangle, this is the base, and these are my limits of integration. So that's how you'd set one of these up. Now we'd use U-substitution, and I'm going to change my variable here right away. I'm going to change my limits of integration, I should say. So we're going to let u equal x squared, du would be 2x dx. So I'm missing a 2, so I'm going to compensate with a 2 on the inside with a 1/2 on the outside. And then my limits of integration, if x is equal to root pi, this means that u would equal pi because I'm going to square pi. So root pi squared is pi. Down here I have x equal 0. 0 squared is 0, so u would equal 0. So now my new integral, 1/2 on the outside, my limits of integration go from u equals 0 to u equal pi. This 2x dx is my du. Sine of x squared is sine of u. So this looks like the sine of u du. So drag the 1/2 along. The integral of sine is negative cosine. So I dragged along the 1/2. The integral of sine is a negative cosine. Now if you want to check that, the derivative of a negative cosine is a positive sine. I don't have to change my limits of integration. I don't have to convert back to x. I have everything ready to go here. I let u equal 0 and I let u equal pi, and I evaluate. I'm going to pull the negative 1/2 out front. I'm left with the cosine of pi minus the cosine of 0. So the negative 1/2 is out front. Cosine of pi is negative 1. Cosine of 0, so here's my negative 1 for the cosine of pi, minus, because I'm subtracting, the cosine of 0 is 1. So I have a negative 1/2 times negative 1 minus 1 is a negative 2. 2's cancel, negative times a negative is a positive 1. Okay, so that's telling me that my net area is going to be equal to 1. So that's another instance where we had kind of a story problem set up where we had to write our own integral, and then after that integral was written, then I could go with my U-substitution, and on this one I did a change my limits of integration right away. But to me it doesn't matter which one you do as long as you show your work. So U substitution is fun, change of variable is even more fun, but now we can talk about using two or more U substitutions to make a problem work. We've been doing quite a few trig functions lately, so let's go ahead and skip into something that's not a trig function. Let's look at the limit of, let's do radical. Let's do something that looks a little dicey. Let's look up 4x minus x root x dx from 0 to 16. So a couple things here. I have a radical embedded in a radical. So I want to start with the U substitution. Looks like I have a couple of options here. Let's go ahead and start with U equals square root of x. Okay, so this is the same as x to the 1/2. So when I take its derivative, I bring the 1/2 down. Let me rewrite that so it's legible. I bring the 1/2 down, decrease the exponent by 1, and then of course the derivative of x is dx. So rewriting that, I have du equals 1 over 2 square roots of x dx. Now it looks like I don't have this. It kind of looks like this is not going to work, but let's keep kind of plugging away at it and see if we can get something to sub back in, because that kind of seems like the natural substitution that we'd want to make there. Now usually we can sub in and we'd have a du and we'd compensate. For this one, let's do something a little different. Let's go ahead and solve for dx. For dx, I'd multiply top and bottom by 2 root x, and I'd be left with 2 root x du. And that's a direct substitution that I could make here then. Let's also change my limits of integration. So if x is 1/2, if I have x equals 16, that would imply u is the square root of 16 or 4. And over here, if x is 0, that would imply the square root of 0 is 0. So let's go ahead and see what we have. I'm going to put u equal on here because we're going to have another substitution. I'm almost sure of it, but let's see where we end up. Okay, so as we're trying to sub in, it looks like to me we'd have our square root sign here. I'm definitely still going to have the 4 there. That's not going to change. Okay, now I have to figure out how to sub in for the rest of this. I have a 2 root x. I can see here that I have a radical x, so I could sub in for part of that. But I don't know what an x is. I don't know what a straightforward x is. So let's go ahead and look over here to see what we can do with this substitution. I know that u is equal to root x. So if I think down here, root x is equal to just u. So this is equal to 2u du. So that would give me a little something to go by there. So dx is equal to 2u du. Okay, so I'm still over here though. I need to do something with this x. I know u is equal to the square root of x. So if I squared both sides, that would tell me that x is equal to u squared. Okay, so I think I could put a u squared then, because x is equal to u squared. This x is also equal to u squared, and this root x is equal to just good old u. So I think I've got everything kind of switched over now. Let's see what we're missing. I think that we've got everything. Let's look at that 2 real close, that 2x dx. I think I've got everything now. So let's go ahead and rewrite this. I think I'm going to be able to pull this 2 out front. Let's do u equals 0 to u equal 4 square root of 4u squared minus u cubed. Then I have this 2 that I could pull out front. This u, I can't pull outside of the integral, but I can certainly put it in front so I don't lose track of it, du. So now I'm ready to integrate. No, not really, because this doesn't look too much better. Let's go ahead and look at the u squared minus u cubed. I could factor out a u squared. I'm going to keep my u equals 0 to u equal 4 because I think we're about ready to do another change of integration, limits of integration. So we need to keep track of what's x's and what's u's. So if I look under this radical, there's a u squared that's common. If I factor out a u squared, I'm left with 4 minus u du. The square root of u squared is u. So this piece would be u, square root of u squared, square root of 4 minus u. Ah, this is finally looking a little decent. So rewriting, and again, keep your u equals 0 to u equal 4. U times the square root of u squared is u squared, root 4 minus u du. Now I'm ready to integrate this, but I'm going to have to use another substitution to do it. I'm going to have to let w equal that radicand. Now I can let w equal the radicand, or I could probably let it equal the entire root, but I'm just going to let it equal the radicand to start with and see how it goes. So w equals 4 minus u. dw would equal to a negative du. The derivative of 4 is 0. The derivative of a negative u is a negative 1. These are fun. Okay, so if u equal 4, 4 minus 4 is 0, so that means w equals 0. And then down here, if I have u equals 0, 4 minus 0 is 4. So I've flipped my limits of integration basically. They used to go from 0 to 4, now they're going from 4 to 0. Okay, so we've got a lot going on here. So let's write what we have. We have 2. Now my limits of integration are w's. W equal 4 to w equals 0. Now u, this says I have u squared. Okay, put that in. So this is 4 minus u, which we know is w now to the 1/2. du, I need a negative du, so I'd have to multiply by a negative inside, compensate with a negative on the outside. Let me do that actually over here in this step. So I have my negative du would be dw. So this looks pretty good except for this u squared. Now let's think about that u squared. W is equal to 4 minus u. So if we solve this for u, we get u equal 4 minus w. So I can make that substitution. W equal 4 to w equals 0. U squared is 4 minus w quantity squared times w to the 1/2 dw. Now we could actually do, that'd be kind of fun, we could do another change of variable. We could let u equal 4 minus w and then kind of work from there. But I think a simple thing to do would be to go ahead and expand this to kind of get out of here because things are getting a little deep. And then distribute through the w to the 1/2. So this would be 16 minus 8w plus w squared times w to the 1/2 dw. We would distribute through the w to the 1/2. W equal 4, w equals 0. 16w to the 1/2 minus 8w to the 3/2 plus w. Now this is 1. 1 plus 1/2 is 1.5 or 3/2. This is 4/2. So if I add 1, I'd get 5/2 dw. Now I haven't integrated this. Let's go ahead and do that. So this would be 16w to the 3/2 divided by 3/2 minus 8w to the 5/2 divided by 5/2 plus w to the 7/2 divided by 7/2. Now we could evaluate this right now, but I don't think I want to quite yet. I think I want to flip these around and do some simplification, just a little bit of simplifying. So this would be 2/3 times 16w to the 3/2 minus 2/5 times 8w to the 5/2 plus 2/7. I'm just flipping everything. When you divide by a fraction, you multiply by the reciprocal. And you can see here then I have these 2's I could pull out. So that's negative 4. And I could also pull out a w to the 3/2. So if I pull out a 2 and a w to the 3/2, I'd be left with 1/3, or actually 16/3 for my first term, because I pulled out a 2w to the 3/2 minus 1, actually minus 8/5 w to the first, because I pulled out a w to the 3/2, plus, I pulled out the 2, so I have 1/7 w. I pulled out to the 3/2, so I'm left with squared. Now, I think this looks better. You might not agree, so you could have evaluated up here, but I kind of like to get these simplified quite a bit before I plug numbers in. So I definitely could find a common denominator here, and I could also rewrite with a positive leading coefficient. My common denominator would be 3 times 5 times 7. So I'm multiplying by 5 times 7 on the top. And here I'm multiplying by 3 times 5. I'm multiplying by what I'm missing. And here I'm multiplying by, actually this would be 3 times 7. And this next one I'm missing the 3 times 5 on the bottom. And this is all over 3 times 5 times 7. Okay, so we have a negative 4w to the 3/2. Now in the denominator I have that 3 times 5 times 7, so that's 15 times 7 is 105, so I can pull that out front. And then up here I want to have my leading coefficient, so 3 times 5 is 15w squared. 8 times 3 is 24 times 7 would be 168w. Then on the bottom I have 16 times, or sorry, not the bottom, on the far left I have 16 times 5 is 80, and then of course 80 times 7 is 560. I think I've simplified this as far as possible. Now we want to go ahead and finally evaluate this, and I don't even remember my limits of integration anymore. W equals 4 to W equals 0. Now I know 4 is the larger number and it's on the bottom, so this might throw you, but we're going to leave this exactly as is. We're not going to try and flip these around. If we did flip these around, remember all we would have to do is negate it. I could go W equals 0 to 4 and then negate over here. So I have this negative 4 over 105, which is the coefficient. And then I have to plug in this w to the 3/2. So I'll have 0 to the 3/2 times 15 times 0 squared minus 168 times 0 plus 560. That's my upper. Now let's go ahead and subtract out my lower. 4 to the 3/2 times 15 times 4 squared minus 168 times 4 plus 560. Okay, so this is negative 4 over 105. And we're trying to simplify this. I'm going to end up with 0 times anything, of course, is 0, so my upper limit of integration is 0. Minus, now 4 to the 3/2, the square root of 4 is 2, 2 cubed is 8. So I'll have 8 times, now my first value here is 15 times 4 squared. That would be 15 times 16 is 225 plus 240. Minus 168 times 4 would be 672 plus 560. So I have negative 4 over 105, and I'll have a negative 8, and I'll go ahead and just combine all those terms in that parenthesis. So a negative, or sorry, 240 minus 672 plus 560 would equal 128. Now I'm getting this down almost to something I might be able to reduce. 8, 9, 10, 11, no, not yet. So let's go ahead and multiply straight across the top. A negative times a negative is a positive, so I have 32 times 128. So I have 4096 over 105. Now 4096 over 105 does not reduce. I don't see any common factors there off the top of my head. So not reduced, that is your final answer. So we're getting some pretty big numbers there, but they are doable. We can do long multiplication real quick with some of those. So this is a very doable type of problem. Now, as you can see, if we're working through these problems, they do get a little long. You don't want to skip any steps. You don't want to drop any of your notations because it's hard to go back and find where we were at. We started with x's, we converted to u's. We had to do a quick little change of variable in here. We changed our limits of integration to u's. We have another substitution, so we switch from U's to W's, so I changed my limits of integration again. And then I simplified the heck out of this thing after I actually integrated it, because I did not want to plug in my upper and lower limits of integration into this, because, well, there's two schools of thought here. First of all, if you plug it in here, you might not risk making algebra mistakes lower, but if you plug it in here, it's very complicated to plug it in and you might make some arithmetic mistakes. So by the time we got to the end, we did get our 4096 for our solution. And I think you could probably check this one on your calculator because we do have a definite integral, but it'd be kind of hard to plug in. But again, you're welcome to go ahead and check those answers, but it's the work that I'm looking for. So please make sure you show all of your work. As usual, if you have any questions, please let me know. I'm happy to help.